this video, I would like to describe the philosophy of the FANTASIA architecture, so describe the motivations that led to FANTASIA being organized as it is, because FANTASIA has been built as a research tool, can be used to build simple conversational AI applications, but its true goal is to support a specific way of investigating how conversational AI may work, which is slightly different from the mainstream applications that we see with large language models, although it has, of course, a relationship with large language models. So the basic motivation behind this video lies in explaining why we do things as we do. And why is a very important word in this presentation, because we will talk about why machines should choose to talk. So we have raison d'exprimer, where language is described as between form and motive. So before describing the actual technology, we need a little bit of background, research. And let's summarize how AI in general has evolved in the last decades. So AI has evolved from rule-based AI, based on logical systems, inference engines, expert systems, etc. And once the limitations of these models have become evident, especially with the relationship to the physical world, which is extremely noisy in representation, in detection, etc., we have gradually shifted to a probabilistic representation, of which deep neural networks are the peak technology nowadays. We also know that probabilistic AI has its own limitations. The amount of data needed to train the most advanced models is huge. Explainability is a problem. Reliability, as we have seen with large language models, is a problem with hallucinations, etc. So one interesting point that we can make is that, okay, we have neural networks, they solve a lot of problems, especially dealing with the physical world. But should we do everything with neural networks? There were many advantages in old school approaches to AI that we may try to recover and integrate with the probabilistic framework that is nowadays popular to obtain hybrid representations. So starting from solid state, rule-based state, we observed sublimation of these AI systems into probabilistic systems. We can now try to move to a more liquid situation when we try to take the best of both worlds. And this is why FANTASIA was born. So language, as Turing observed in his days, and the capability of conducting dialogues is an important capability for intelligent systems. But we need to be careful in differently modeling language with respect to modeling communication. So large language models can capture conversation dynamics, but they do not necessarily capture the motives behind them. So why did a certain person say something? Large language models can quite efficiently predict what would a person probably say next, but they don't necessarily model why they said what they said. Being based on machine learning, they capture regularities and correlations, but cannot model causation. There is a discussion actually going on about this, whether they do model causation or not. Personally, I tend to think that they do not model causation explicitly. They only appear to do that in certain situations. But still, discussion is ongoing. Predicting the most probable utterance, given what people usually say, so given the training set, and presenting it as a position of the AI is, in my opinion, wrong. This is because the model will only predict what would probably follow the prompt and the history of the dialogue. So the idea of saying that the AI position is the most probable one that would be observed in the training set actually doesn't match what's happening in the model. It's only a question of saying whether the AI is reporting what people would probably say against presenting a position of an intelligent agent. These are two different things, and we cannot mix them up. Concerning the motivations of language, choosing to talk or even not to talk serves purposes. So predicting language is not the final goal of our activities. Language is not just an abstract sequence of symbols to be predicted. Even all the research that is being done with grounding language, so training systems that take into account images, audio, so physical signals to improve the quality of semantic representations, is proof of that. Being able to consider, if not understand, the consequences of its own actions is a necessary step for machines to produce language with actual intents and to avoid harmful content. So we know that large language models are extremely biased. There has been observed cultural bias, gender bias. This is simply because the amount of material, of linguistic material they are trained on is overwhelmingly favorable to certain positions rather than other ones. And this underlines the fact that these are statistical machines, not really intelligent machines. So they don't understand the consequences of their actions. They just predict what's going to follow next. Machine learning is only one of many powerful tools to understand language and human behavior in general. So yes, they solve a lot of problems, but they're not the only tool in our toolbox. So presently, dialog flow is conducted more or less as we see. We have ASR in speech-based dialog systems. The transcription is given to the large language model that generates an answer, and we synthesize speech based on that answer. The idea behind FANTASIA is to avoid having large language models implicitly take decisions that they don't seem able to understand. So before moving to the large language model, we need to have an explicit representation of the state of the dialogue, which is different ways of representing common ground. We need to have a dedicated module to decision making that informs the large language model about what to say. So we are not discarding large language models, we are trying to put them into the correct frame. This is because generative AI, in our position, is good for natural language generation, but not for dialogue management. So large language models can produce extremely fluent, correct, and even contextually correct sentences, variable sentences, pleasant sentences from this point of view. And they actually solve a very hard problem, which is natural language generation. So it is not easy to generate linguistic content. We have seen many cases of dialogue systems producing template-based sentences. It is hard for dialogue systems to use, for example, pronouns or references to things that have already been said before, either from the system or from the user. So in this model, large language models have the role of generating coherent and fluent language. But the process of deciding what to say is not performed inside a large language model. It is a step that comes before. This adds control, explainability, and even has the potential to reduce the amount of data that is needed to train the language model. because many things that currently we are trying to do with large language models may be moved outside into dedicated modules and interpretable models. From a philosophical point of view, the idea that is behind FANTASIA lies in the declaration, the manifest of technoethics. So when art is a form of behavior, software predominates over hardware in the creative sphere. Process replaces product in importance, just as system supersedes structure. So in this view, intelligence is more about the process with which we produce results, rather than results themselves. Big data, large language models generating coherent content that follow a prompt, leverage on our instinctive tendency to attribute intention to communication. We are used at reading text that someone wrote with a specific intention in mind. We have never seen text that has been generated from a machine, so we tend to attribute communicative intention to what we read. But tricking humans with fluent and coherent content that doesn't have intentionality is possible. So there is probably no intention in large language models, because they're simply generating what would probably follow. And this, in a sense, tries to hack the measure given by the Turing test about having intelligent behavior, which does not necessarily correspond to solving the problem. In general terms, we have the risk of being tricked by the illusion of agency, which is something that has become evident even in the old days of AI, with the experiments conducted by Valentino Breitenberg concerning the Breitenberg vehicles. So in this nice book about vehicles, experiments in synthetic psychology, simple wired vehicles were proposed that could model behavior that may have been considered intelligent by the external observer. These vehicles only had reactive capabilities, so in the figure we can see a vehicle that has photoreceptors connected to an engine, and the engine would make the wheels turn. By simply inverting the connections, the two vehicles would exhibit different behaviors. One would have an avoidant behavior concerning the light, and the other one would have an attraction behavior towards the light. The external observer may be tempted of describing these behaviors as intelligent, as intentional. One vehicle will be looking for the light, may like the light. The other one would be avoiding the light, being scared of the light, etc. Nothing of this is present, of course, in these vehicles. No cognitive capabilities are present in these vehicles, but there is a risk of ourselves attributing these traits to artificial agents that we observe. Machine learning is very good at cleaning data by recognizing underlying patterns inside noisy channels, which is something that old school AI was not capable of doing. We just have to ask ourselves if neural networks, being connectionist models, are very complex Breitenberg vehicles. Are we being tricked into thinking that these models are intelligent when they have no actual intentionality? Can a machine be intelligent without intentionality, without wanting to do something? We have to ask ourselves if, when we look at machine learning items hallucinating, we've seen this in many cases recently, it is not actually us that are hallucinating into thinking that we are dealing with an intelligent agent, or even with an intentional agent. An alternative theoretical framework that goes beyond neural networks is summarized by the ladder of causation from Julia Pearl. In this model, machine learning resides on the lowest ladder, which is only concerning with observational capabilities, observational and predictive capabilities. The question is, what if I see? What should I extract if I see a certain thing happening in the world? In this sense, machine learning is only an external observer of the world, and it doesn't actually understand its own world, what it's actually doing when it produces, for example, linguistic acts that we need to consider as actions. So machine learning based agents are passive observers and only react to it, but they do not act in it. Modeling the effect that acting in the world provides, including speaking and confronting the consequences, allows to generate language for its intended purpose. So the machine would start talking with the intention of altering the world of which it is part of. On the third level, imagination, the capability of retrospective reasoning is a fundamental ability that relies on causal modeling capabilities. So we need to move from the first layer of the ladder to the second, and in the future on the third. At present, research that we are conducting with FANTASIA mainly concerns the second level of the ladder. And some of you may remember something like this concerning movement on the causation ladder. This kind of representation has interesting connections with the computational psychology representations concerning, for example, emotions. The capability of combining probability and causal reasoning can be connected to emotional feedback. So, for example, in the work of Micheli and Castelfranchi, the concept of interested anticipatory representation, so prediction that is combined with what I would like to observe in the world, can have an important role in the elicitation, in the creation of synthetic emotions. Surprise, for example, may arise from the belief of possibility, so believing that it is possible that a certain proposition P is true, and collecting evidence that denies, that negates this belief, generates surprise. So I believe that something is possible or even probable, but evidence from the world tells me that this is not true, and this surprises me. When we combine this with the belief that something is not possible, combined with the fact that we want something to happen, so that P is our goal, we have, again, surprise. We didn't think that something was possible, and we wanted this something to be possible. We actually observed that this something is possible or true. So we are surprised by this. On the other hand, if we believe that something is possible or probable, and this is our goal, but we collect negative evidence contradicting this positive IAR or this positive expectation, again we are surprised and disappointed, because we wanted something to be true. We thought that it was possible that this would have become true, but evidence from the world tells us that this is not actually true, so we are disappointed. This kind of representation is important to introduce in our systems fundamental drivers to act. And we can take psychological theories describing mental needs to motivate why the machine should choose to act in terms of generation of linguistic content. This can even go beyond that if we introduce counterfactual reasoning, to the point that we have something like what will happen when I will look back at this decision and consider what would have happened if I acted differently than what I am considering. So predicting the moment in which we will have to do counterfactual reasoning when we are actually producing the fact, taking the decision, is one of the extreme points that we can reach when dealing with this kind of representation. Actually, this has nice connections with the Monty-Hall problem. So language is a tool. Language is not the end product. Language is a means to an end. And historically, of course, language has been used to shape the world. Language has been used to inspire people. Language has been used in fiction to elicit emotional reactions. And yes, language can be used for evil purposes too. So we need to be careful when we deal with language, because language is a tool, and it's actually a very powerful tool that can be used to do a lot of good, but can be used to do a lot of evil things too. So concerning the amount of AI technologies that we have to conduct dialogues, as we said, neural networks are not the only choice. They are one of the tools. So let's try to put things into context and try to understand what we can use in FANTASIA to implement different capabilities in our systems. So machine learning is good for pattern recognition, to generalize, and for behavior synthesis. In general, machine learning is very good at dealing with the physical world, with the real world, and extract or put things in the real world. Then we have graph databases, which are a modern technology, very powerful technology, that we use for knowledge representation, deductive reasoning, and knowledge filtering. In this sense, graph databases are a way to recover the capabilities that were introduced by inference engines, so deductive reasoning in terms of path search. Then we have behavior trees that we can use to prioritize tasks, to synchronize subsystems, and optimize behavior, so avoid activating useless behaviors if more important behaviors are active. And then we have Bayesian networks, but in general probabilistic structural models, graphical models, that we use for decision making, utility estimation, and to implement goal-oriented behavior. In general, machine learning is trained machine learning models are quite mysterious in a sense. They do their task, they are quite obscure about how they do it. While we can access linguistic or even psychological theory to organize explicit models driving the behavior of the AI. The role of graphs in this sense is particularly important. They are very good at representing data in a human interpretable way. They are backed by considerable math, because graphs are a very old mathematical tool. They can be projected in numerical spaces for the machine to work with. So they are a very nice bridge between the needs of the human and the needs of the machine. They can represent a modern way to recover inference engines, and since they are trying to be included even in large language models, they cover a very important role into providing support for grounding and explainability, and even to avoid what have been called hallucinations. Embeddings are also very important for this kind of technology. We can rely both on text embeddings and on node embeddings, and the combination of the two can be very important into building complex graph structures that combine both catalographic information and textual descriptions into a single number-based representation. So what is in general the role of graphs? We can consider the graph as representing the state of the dialogue. both at the same time the state of the dialogue and the amount of knowledge that is possessed by the agent about the domain it is talking about. The configuration of the graph, we can try to check for definitions of graph configurations that tell us what we should do, what the system should do to alter the configuration of the graph. So in this sense, language is an action that is intended to alter the graph representing the state of the situation, representing the state of the world. So a graph may be uninterpretable if any of the graph patterns describing each of the foreseen communication problems is activated. In these cases, a clarification request is produced. If a graph is interpretable, it may be incomplete if information needed to respond to the user is missing. In these cases, a request for information is produced. A complete graph may be incoherent if logical conflicts are found in the belief graph. In these cases, the adequate disambiguation question is produced. A coherent graph would be unstable if there are open issues, like for example unanswered questions. In this case, a question answering strategy must be activated, so we cannot do anything we want, we just need to respond to what the user said. If the graph is stable but undesirable, it means that it doesn't exhibit a goal pattern. So we can try to express goals as patterns on the graph. So the goal of the system would be to alter the graph to try and make it so that the graph exhibits the goal pattern. So in these cases, the most useful dialog move would be the one that maximizes the probability to observe the goal pattern in the graph. Like for example, an exploration or an exploitation move for the case of recommender systems. Desirability is therefore important in our definition because it introduces the concept of goal in these systems. So the system will try to produce linguistic acts that are meant to create a pattern in a graph. So the system acts with a goal. Machine learning is often used directly to take decisions, but in general, we know that it tends not to be reliable when producing decisions. Embeddings and score capture semantics in a very broad sense. They are very good at filtering, for example, but they're not very good at going into the details of the similarities between objects that have similar embeddings. They are typically considered difficult to explainable, but we can also provocatively say that maybe they are even too explainable because the explanation is always the same. This is the most probable output given the training set and the stimulus that you are providing to me. Can we use this kind of strategy instead of producing the answer to reduce the amount of data on which to apply interpretable AI approaches? So first of all, we need to be able to build graphs that represent the dialog state as this evolves. As for example, in the movie recommendation task, we may have a situation in which the system presents itself. Hello, my name is Jason, are you ready? And the user says, yes, I would like to see an action movie. Now let's assume that we are using a machine learning strategy to extract intents and entities using natural language understanding tools. So we would have, for example, an intent get by genre, which has a slot subject to which the word action is assigned to. And the word action is an item of type genre. This sequence of steps produces the graph in the figure. So the word action is a named entity of type genre. The word action is the same as the concept action genre. So we have a difference between the named entity and the concept of genre action. The utterance uttered by the user expresses an intent instance that is a get-by-genre intent and refers to the action named entity. Then the get-by-genre intent has a slot subject and the named entity action has been assigned to it. Next, the get-by-genre intent implies that the speaker is trying to create the belief once, where the predicate is what has been assigned to the slot subject. This is why we need intent instances. So the system creates a new belief, just duplicating the belief node implied by the intent node, that the system believes the belief once with the user as subject and then as predicate the action genre because of the intent instance. It is always important to keep track of where did some beliefs come from, even to compute their strength, their importance. So this is a way to dynamically assemble a graph that connects the dialog representation with the knowledge representation, because we have the action genre node, which is part of the domain knowledge, and all the rest here represents the dynamics of the dialog. So where did certain beliefs come from and how did the dialog unfold? We need now to make decisions about what to say. In Fantasia, through the Agrum library, we include Bayesian networks, and in the next update we will also have influence diagrams. Bayesian networks are very powerful for decision making, and they are able to take into account all the data that is needed to take decisions. For example, machine learning performance on test sets can be used as priors. So we can reason about what would probably be true without observing anything about the world, and they efficiently separate priors from evidence. Influence diagrams, on the other hand, are explicitly dedicated at choosing actions given the information that we have about the world, the probabilistic information that we have about the world. They separate what we predict about the world and what is true about the world at the time when we need to compute the utility of our decision. These are both very simple examples that you can find described anywhere, so I will not go into the details of this. One of the problems with probabilistic graphical models for decision making is where do these models come from? So one advantage of these models is that they can be dynamically assembled, as opposed to neural networks, in which once we have decided for a certain structure that doesn't change, we can dynamically generate Bayesian networks and influence diagrams for decision making. The point is, how do we assemble these models? And this is a fundamental question when dealing with this kind of models. In our approach, we try to exploit the structural similarity of knowledge graphs, graph databases in general, and probabilistic graphical models. So they're both represented in terms of graphs. So the fundamental task for decision making becomes extracting from a very large knowledge graph a relevant subgraph that we can populate with priors, evidence, etc., to decide what to do next. In loose terms, it is there is a parallel that you can do between about the difference between long-term memory and working memory. So we do know a lot of things about the world, and we have a very large knowledge graph, but once we need to decide to do something, we only reason about a small part of what we know of the world. A relevant subgraph is relevant with respect to the dialog context and to the goals that the system is trying to accomplish. Efficiently extracting these subgraphs is an important task, and probably Vector indexing, which is a feature that has been recently introduced by Neo4j and that is in general a capability of modern vector databases, has the potential to be very relevant for this task. So we need to efficiently extract a subset of information, study its structural organization inside the knowledge graph, and use this structural organization, for example, by considering ontological relationships. We are concentrating on part of relationships at the moment, to convert the subgraph, the relevant subgraph, into a structural causal model, or a Bayesian network, or an influence diagram, etc. So into a probabilistic graphical model for decision making. So this is an important step that we are working on. So the connection between knowledge graphs and probabilistic structural model, using efficient queries to extract relevant subgraphs that may now leverage also on the technology provided by vector indexing. So why the system should choose to speak or not to speak? It may choose to speak or to stay silent depending on desires. So the graph representing the situation I'm part of is not what I want to be. What is the linguistic act that maximizes the probability that the desired graph configuration will appear? Then I try to push the configuration of the graph towards the one that I desire. Competence. So the system realizes that it is not confident in predicting what is going to happen given the current graph configuration. So the most useful thing to do is ask a question to collect more information about the situation, to populate the graph more and improve the prediction capabilities. Curiosity, which has to deal with fundamental theories in computational psychology about motivation. So the system realizes that the current graph configuration probably contains missing information. Can I ask a question to complete it? It is very probable that I'm missing a node, that I'm missing a relationship. Can I ask a question to confirm that this information is missing and collect it? And then counterfactual reasoning. So things went differently from what I expected. What would have been the graph configuration if I did something different in the past? Now that I have more information, I can try to reason about my past decisions, imagine what would have been the outcome of different decisions, and learn from this. This is the third level of the ladder of causation. Lastly, we have behavior trees. So behavior trees organize small tasks and only execute tasks if they are actually needed. In this case, we have an example about the belief graph update. Once we have a coherent, an interpretable graph, we update the belief graph and we check for incoherence. So we open a transaction in a database, a temporary update to the database that is not yet committed. And we try to check if we can observe in the updated database an incoherence between bias and evidence. If we actually find this incoherence, then we roll back the graph and we ask a clarification request. Otherwise, we continue and we commit the update because it doesn't introduce an incoherence in the belief graph. And we move to dynamically assembling the Bayesian network. We collect the beliefs, so the data that we already collected during the dialogue. We apply evidence to the Bayesian network, and we are able to take decisions using the model that we just assembled. So in general, this is the processing that we try to develop in our research. We have, first of all, a perception layer, mainly produced with machine learning, so automatic speech recognition, intent recognition, entity recognition, etc. We have an internal modeling phase in which we represent the dialog state in a graph form. We perform interpretability, coherence, stability, and desirability checks. And then we move to decision making. We use embedding-based data filtering to extract relevant subgraphs. We assemble Bayesian networks, but in general probabilistic graphical models. We use utility-based action selection, select potentially supporting features, for example, to support argumentation capabilities, and then we use large language models for natural language generation. So once we decide to say something with a template sentence, for example, we then use large language models to convert this template sentence into a contextually coherent sentence, contextually from the point of view of the dialogue. You can refer for more information about this to the tutorial about using OpenAI into FANTASIA. And at last, we have the actual action layer, again performed with machine learning only, where we have speech synthesis, so TTS, and possibly non-verbal behavior. If we are dealing with an embodied conversational agent, we may need to use gestures or facial expressions and so on. So at this point, you should have a better understanding of the reasons why FANTASIA is organized from an architectural point of view, as you can see here in this slide. FANTASIA, again, can be used to implement systems in other ways. For example, it is possible to build a system that is only based on large language models in Unreal using FANTASIA. But in general, the intention of FANTASIA is to investigate the kind of approach I just presented you, and the kind of approach that we are working on in the lab. Many of these things are still under investigation, but the point is that FANTASIA is a tool designed to let people play around with this kind of approach. It is a tool designed to let people test theories, linguistic theories, psychological theories, etc., in the field of conversational AI. So it's not only meant to support people into producing useful tools. It is a framework that is meant for researchers to investigate about intelligent tools. So the equivalence between useful and intelligent has been recently popular is not correct in my opinion, but it is good if you want to build something that simply provides a service to use FANTASIA in this sense. But if you want to understand if a certain theory about psychology, about linguistics, etc., concerning dialogue management works as a formalization of intelligent behavior, FANTASIA has been designed to support you into doing this. In general, I will give you an overview of the Metafamily that we have at our disposal to investigate different kinds of conversational capabilities. So Maya is an agent that is designed to provide spatially aware presentations in 3D environments, typically semantically annotated 3D environments. Then we have Bastian, which deals with the cooking domain and has been built to investigate common ground inconsistencies in the past. And there is Jason, that you also may know from the tutorial, which is our meta-human that is used for user profiling and recommendation in the movies domain. So to conclude, modern AI provides great tools to project physical observations in n-dimensional numerical spaces, which can represent the mind of the machine in a very loose sense, a space in which the machine can reason, also considering nuances in meaning. A machine can only communicate with intention if it is given the chance to explore and learn about the consequences of the action of speaking. Psychological theories about motivation and emotion provide drivers for the machine to evaluate what speaking or not speaking implies. Research is maybe too much oriented at depleting the mind of every technology that is presented. There are lots of papers showing the applications of new models and little research about the reasons why these models work or even appear to be working. There is a commercial push towards brute force approaches. Only the big players have the strength to support this kind of approach, so democratization of AI is a problem. Computer science is maybe the most introspective among hard sciences, so developing machines that talk can help model intelligence, describe formal models of intelligence, and build tools to stimulate thought through unbiased dialogues. So in general, we can view the investigation research about conversational AI as a way to understand if our theoretical formal models to describe intelligence actually produce intelligent behavior. Not necessarily human-like behavior, but intelligent behavior in general. So, thank you for listening. I hope this description of the intention behind the development of FANTASIA has been useful for you, at least for understanding why FANTASIA is organized as it is and the kind of work that we are doing. And I will see you hopefully at the next video.